Okay, so the second part of this talk, and then I'll quickly finish with the predictions for the next 100 years.
Well, that's bloody good for today, wasn't it?
I know your type. Right. So this is a brief outline of what I want to do. Colour-coded, as it were, into 3 bits. The first bit, in some sense, we've done, so we'll be pleased about that. Just to remind you, we had a discussion about Bell's theorem and the whole issue of non-locality, which of course was what Einstein hated about quantum mechanics. And well, he had some ideas about the role non-linearity might play. And Basil and David wrote a paper in 80-81 expanding on that. And I tried to sort of develop that further with some ideas from, let's say, sort of modern day theory about chaotic dynamics or deterministic non-periodic dynamics, as I called it. The basic idea being to just remind you to think, you know, if the universe were somehow governed by a system of this type, if the equations of physics described one of these systems on its invariant state, then because these are basically zero-measure, low-dimensional objects in state space, any type of, you know, to use Michael's word, counterfactual perturbation, which might be one where you say, well, given that I've measured the position of this particle, what would have happened if I measured the momentum? Any question of that sort is basically meaningless, because with probability 1, that type of perturbation, that type of thought experiment, or perturbation associated with that type of thought experiment, would take you off this invariant set into a part of state space where by construction your physical system is undefined. So I think it presents a perspective on the conceptual problems of non-locality. However, what it doesn't do is tell you how you can kind of marry quantum theory as we understand it today, and which is clearly a successful theory of physics. You know, it doesn't tell you how you could marry, in some sense, quantum theory with this type of system. So that's really what I want to do in this talk. I'm conscious that, you know, my level of mathematical sophistication is nothing compared with Freddie and Maurice's. So I'm kind of groping, in a sense, for trying to express ideas that I have in my head into mathematically kind of into a mathematically coherent framework. But it's very much a you know, at a sort of somewhat rudimentary level at the moment. But nevertheless, maybe I can convince you there might be something in it. Now, the black bullets are trying to just continue with the discussion about nonlinear dynamics. And I want to talk about this thing called symbolic dynamic representations, and introduce a very fundamental thing in dynamical systems theory about a kind of duality between the conventional state space representation of dynamical systems as things like differential equations, and what's called a symbolic or symbol space representation, where you represent dynamics by strings of symbols, often just binary symbols. And indeed, many of the properties of dynamical systems are based on, or certainly most easily proven in using these symbolic representations of the nonlinear dynamics. And I mentioned, perhaps briefly yesterday, things about synchronization of oscillators, and again, symbolic dynamics provides a very kind of simple way of thinking about that. And then I want to just refer briefly to some linear structures which actually exist in symbol space, notwithstanding the fact that the underlying system is nonlinear. I then want to go on to try to take kind of conventional quantum theory and see to what extent it can be developed in this symbol string representation. So to what extent we can think of quantum states as symbol strings. And again, I'm going to very much draw on this duality between the symbolic dynamic representations and the state space representations here. So we'll go through a bit of that. And then the final bit is to try to kind of marry these two bits together and come back to this issue about entanglement. And this will lead me to think about entanglement as a dynamical process, and in particular as a reduction, as a dynamic reduction in the dimension of this underlying attractor, which is somehow governing the dynamics, and then to think about that as gravity and stuff. Then we'll finally finish with some of the links to Penrose's ideas. So I would say I am fairly sympathetic to a lot of Penrose's speculations, but I've kind of turned the logic of some of his arguments around, on their head to some extent. So I have a different take on his ideas, and it's to do with actually thinking about entanglement, large-scale entanglement, as a manifestation of gravity as a large-scale manifestation of entanglement. Anyway, so that's the outline. Symbolic dynamics, it's probably easiest to think of a specific example, and a very familiar, a very rudimentary example of a system which has chaotic behavior is just the logistic map. So you just iterate on the real line some real number x with this function f, which is just a quadratic. Now, the whole, books and libraries have been written about this equation, and there are various, and some of the sort of Tom catastrophes can be viewed in terms of bifurcations as mu increases from 0 and above. Well, I just want to consider, just for illustrative purposes, this map when mu is greater than 4. When that happens, if you think about the real line, and imagine this is the interval between 0 and 1, basically anything outside that interval 0 to 1 gets mapped to minus infinity under repeated applications of f. So minus infinity is a sort of an attracting point in some sense. But what I want to consider is, within this unit interval between 0 and 1, what is the invariant set for f? In other words, what points in the real in the unit interval keep within the unit interval under repeated mappings of f? And so, for example, if you took f equals half, then you'll get a half times a half is a quarter. So multiplying by mu, which is greater than 4, will give you something bigger than 1, and then that will map to something negative, and then eventually go off to minus infinity. So this bit, in fact, anything in here will get mapped off to minus infinity. So if there is an invariant subset, it lies somewhere on these two, and then just by just following the analysis, it turns out that what you actually end up with as the invariant set is the classic Cantor set, where you just take away the middle third, and then the remaining, the 2/3, you take away the middle third of that, take away the middle third of that. You can represent a point on this Cantor set by just writing, considering its expansion in base 3 numbers, and if that base 3 expansion only contains 2's and 0's, then you know that you're on the Cantor set. If you take a general point on that unit in the unit interval, then in general it will have 1's as well as 0's and 2's, and those won't be on the set. So in fact, since almost all points on that unit interval will have kind of mixtures of 0's and 2's and 1's, you can say that this